their field domain experts who have delivered the lectures. And this is the 10th one, which is being done physically, and also we have made it as a hybrid mode. The people who are here, they would be listening to our speaker, and also it is open to streaming to YouTube as well as Zoom. And also today is a very momentous day, a very lucky day that today is the National Science Day. This is the day the government of India celebrates as a National Science Day to commemorate the first discovery of the Raman effect by Dr. C.V. Raman. That is 28 February 1928. I think this is a wonderful coincidence that on this National Science Day, we have with us Dr. Ranjeet Nagare. He is from Canada, and would be listening to him and also knowing about him shortly. But before that, I would request our president, Mr. G.S. Kuntia, to come to the dais and give his opening remark.
Good evening to all, ladies, gentlemen. So this is distinguished speakers 10th series. Our secretary has already introduced the background behind this distinguished lecture series, and today is the 10th such program. So it is our privilege that Dr. Ranjeet Nagare, a distinguished lecturer, he is principal hydrological engineer from ARKK Engineering Corporation, Alberta, Canada. And during his visit to Bhubaneswar, we have taken advantage of this lecture series. We will hear from him all about the Canadian oil sands, its mining operation, its processing and refining, and various other things. So I would congratulate him for his state-of-art lecture, and on behalf of SGAT, I welcome him. And we have also another distinguished authority, Mr. Lalu Mansingh. He is with us. He is also a veteran in the field. So oil sands, tar sands, crude bitumen. Before I just start, I would again introduce, I am a mining engineer. I am from IIT ISM, a first class mine manager certificate. My total experiences were in Steel Authority, various Bhilai, Bokaro, Durgapur, Alkala in their mines, corporate office. And I was independent director for last 20 or 24 years in various organizations like NMDC, OMC, and Visakhapatnam Steel Plant, etc. So these crude bituminous sands are various types of petroleum deposits, particularly consolidated sandstone containing natural mixture of sand, clay, and water soaked with bitumen. And it is extremely a viscous form of petroleum. Significant bitumen deposits are there in Kazakhstan, Russia, Venezuela, and in Canada also. And natural heavy bitumen and extra oil differ from ordinary oil sands. It is a form of an unconventional extraction of oil. The cost of production is the only bottleneck. Otherwise, it will solve many of the energy problem in the world. Some of the biggest deposits in these oil sands are in Canada, Venezuela. They are as long as a very expansive area, something like 600 kilometers in length, width is about 70 kilometers. So almost whatever is the world reserve of oil, that much is available embedded in this deposit. So we will hear from him about the mining, processing, refining, and no doubt it will solve energy security problem of today's world. So with all these things, I invite Dr. Ranjeet Nagare and all our distinguished members, council members, and all those who are present here. Thank you.
I now request our Vice President, Mr. Sujit Mahanti, who would introduce our distinguished speaker today. And then he will also inform you about the follow-up meeting and the other details. Thank you.
Good evening, all of you. Respected President, distinguished guests and participants. I welcome all of you. We are really delighted to know that people from different, from industry, from academia, and from research laboratory, they have all gathered here to just to hear a very important talk that is going to be delivered by a very distinguished speaker. So I must make a special mention of the family of Dr. Nagare actually. They are here. Dr. Nagare's parents are here. His wife is here. His mother-in-law is here. So we are really happy and we also welcome you, the entire family, to this August gathering. Coming to the CV of Dr. Nagare, Dr. Ranjeet Nagare was born in an agricultural family in the interiors of Maharashtra near Shirdi. He completed his bachelor's in civil engineering from Pune University, master's in environmental sciences from BTU Cottbus in Germany, and his Ph.D. in hydrogeology from the University of Western Ontario in Canada. He is a registered professional engineer with the Association of Professional Engineers and Geoscientists of Alberta, Canada. Dr. Nagare is a hydrogeological engineer with over 22 years of diversified research and industrial experience in providing solutions to groundwater-related technical and regulatory problems. He has worked on several complex multidisciplinary projects in Canada, the USA, Germany, and South Asia. Dr. Nagare is a highly regarded subject matter expert in the oil sands mining industry in Canada and is an expert numerical modeler and a specialist in the fields of hydrogeology and wetlands and cold regions hydrology. In addition to solving classical groundwater flow and solute transport problems, he has been leading efforts in advancing the mine reclamation and closure of Canadian open pit oil sands mines. This is a brief introduction of Dr. Nagare. With this note, it's my pleasure to invite Dr. Nagare to deliver his talk. But just before inviting, I have one announcement. I'd request all the distinguished participants, both online and offline, to please send your questions, if any, in the chat box only, which is to be answered at the end of the talk. And Dr. B.M. Farooq, former Director, Geological Survey of India, is requested to moderate the question and answer session after the talk is over. Now, moving ahead, I'll request Dr. Nagare to please come and deliver the talk.
Thank you very much. Thank you very much. Thank you very much for inviting me to speak in front of SGAT and all the distinguished members of the association. Not knowing your audience is or can be very, very dangerous, right? So when I was invited here to speak in front of you, all of you, I was thinking what is the most appropriate topic that would resonate with everyone. I come from a very beautiful place in Canada, at the foothills of Rocky Mountains. As you can see, one of the most beautiful places in the world, Banff, is very close to where I live. But obviously, I'm not a tour guide, right? So if to talk about that for 45 minutes is not a very appropriate thing to do here. And Canada and Canada and India are going through very friendly time right now, right? So that's not a very good topic either for the audience. But coincidentally, I'm a geoscientist as well, and we all are in some shape and form. So I basically thought that the most appropriate topic would be to talk about the Canadian oil sands, where I work. I've been working for past 15 years as a hydrogeologist. And keep it as broad as possible. Like my objective is to keep the talk as broad as possible, introduce the Canadian oil sands to the audience, and also the mine closure and reclamation along the way as well. Uh, as uh, as you would have already researched a bit when you saw the topic, right? The oil sands are unconventional deposits that are actually a mixture of sand within which the oil was deposited in the Cretaceous times, when there used to be a shallow ocean, and these basically are are very viscous deposits. That's a mixture of sand, water, fines, and bitumen or tar sand. The bitumen cannot really flow at room temperature. It's highly viscous unless heated, and that's what basically. Uh, yeah. Okay. Okay. They cannot, like, they don't naturally flow at room temperature because they're viscous. So they need to be heated in the processing before they can be upgraded into oil products. Um, the 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 mixture is made up of about 4% water, which actually allows the separation from the soil grains. Otherwise, it will be so tightly bound that it wouldn't be possible to separate the oil or bitumen from the mixture if the water didn't exist. And at its best, it's about 15% bitumen, and at its worst, it's 7%, because whatever is below 7% is not economically viable to recover and to process. So whatever is between 7% and 14% is the deposit that is considered as economically viable deposit for extraction. Just to give you a brief history of oil sands in Canada, in about at the end of 1700s, when the Europeans came to Canada and were doing fur trading in the province of Alberta, they accidentally got to know about the oil sands, which were the bitumen that was naturally seeping along the river banks of Athabasca River, and was used by the native people to waterproof their boats and canoes. As the Europeans took over the country, as it happened all over the world, like in those times, there was a lot of exploration at the start of the 1900s to understand the extent of the deposit and its economical viability. 1978, the first barrel of oil was produced from oil sands, and today about 1.5 million barrels of oil is produced from the Canadian oil sands every day, and that's about 50% of the total oil that Canada produces. Canada has about 173 billion barrels of oil. A barrel is about 20 liters, give or take, of proven oil reserves. 97% of that is in oil sands. So you can see the importance of oil sands to the Canadian economy, because Canada is basically predominantly a resource-based economy. Over half of this oil that is produced and exported from Canada, and mostly it's processed in US, it comes from oil sands. 19% of these oil sands are close enough to the ground surface and therefore are mined using surface mine techniques, and contribute the 19% of that it is through surface mining. About 1,000 square kilometers of area, which accounts for about 0.02% of boreal forests, or what we call the taigas or the coniferous forests, has been disturbed due to these surface mining activities. And about 7% of Canada's greenhouse emissions occur due to the oil sands mining activity. Just to show you where the Canadian oil sands are, where is the pointer here? Sorry. Okay, yeah. So that's North America. That's our, like, India's newest military friend. Not to that, that's Canada, the province of Alberta, and then that's the Fort McMurray area, and the sedimentary basin as shown here, wherein the Canadian oil sands occur. As I was saying, that 19% of it is close enough to the surface and is being mined by surface mining techniques. Anything that exceeds about 75 meters is not economically viable to mine using surface mining techniques, and then is either mined using what we call steam-assisted gravity drainage, wherein two horizontal wells are used and steam is pumped in the upper well that melts the bitumen, which flows gravitationally to the next horizontal well, which is situated below it, or through continuous steam cycling in a single borehole. When you look at the in situ extraction, which is not what we're going to talk about, but is the about 80% of oil sands production, you basically can see in the aerial view oil well pads, wherein these operations, the SGAT or steam assisted gravity drainage take place, and bitumen is extracted using a conventional well and then transferred to a processing facility. But it's the surface mining that I'm going to talk about, because that's the area I work in and my company works in, which I'll introduce at the end of the first section of the talk. How big is this mining operation? Just to tell you that the biggest haulers in the world, the 797 caterpillars, were produced by Caterpillar only for oil sands mining, because the volume of earth material that's moved in these operations was so big that the conventional haulers were not enough. So in 1998, Caterpillar designed the 797 only for oil sands originally, which is now used as the most common hauler all over the world in the mining industry. But to tell you how big oil sands mining is, the surface mining, it is at the moment in an area of about 1,000 kilometers square. It started in the early 1990s, where it would have been about 50 kilometers square, and has expanded to an area that's unimaginably big. This is just to show you some snapshots. Like if you can move that box, like the video box, if you don't mind. Yeah. In 1990, as you can see the scale here of about 30 kilometers. In 1990, you had about 50 to 75 square kilometer area of area disturbed. That has grown to about 1,000 kilometers squared in the current day. Some of the tailings ponds that store the tailings from oil sands mining can be seen from space. That's the amount. That's the nature of the mining that occurs in this area, which is nothing to be proud about, but just to give you a scale perspective. How do the operations occur? The oil sands are a part of the boreal forest, which have about 10 meters of organic soil, which is stripped and salvaged for reclamation purposes and stored in what we call overburden dumps within the mine sites. And then the overburden material, which is all material that exists between the ground surface that I talked about to about the ore oil deposit, that's also mined out and then stored in overburden dumps before the mining of or the extraction of the resource itself can start. As you can see here, the schematic here basically shows the different stages of oil mining, wherein the oil is mined using shovels and shovels that dig into the sand or the oil sands and load the haulers that taken to the extraction plant, where it is mixed with hot water and caustic soda and hydraulically transported to the processing facility, where that mixture is agitated. That agitation brings it up as a froth, from which oil, which is now more mobile, is extracted and then sent to processing facilities to process into various oil products. This picture basically shows compaction of one of the outcomes of this whole process is that because there are, as I said, there's only about 7 to 14% of bitumen in the deposit that's the ore. The rest of it is all stored in tailings ponds as mine tailings, and the mine tailings are massive ponds that store sand from which the oil has been extracted, fines. There are about 30% fines in that one, and tailings water, 90% of which is recycled and used in the processing. As I said, the ore is mixed in hot water and caustic soda. All of that water is again recycled, and oil sands industry basically recycles 90% of the water that it stores in the tailings ponds. The picture on the screen shows compaction of a dike or a dam and the air side of that dam. The next picture basically shows the water, sand, whatever remaining oil that's remaining after processing, and fines being supersaturated and then transported to the tailings ponds and deposited into the tailings pond for storage. And then this is basically a massive beach of sand that's on the water side of the tailings pond that runs for several kilometers at times. So you can basically see it's really flat, but until you reach the water surface, which is here, this is a beach that's being poured using hydraulic techniques and transported in a pipe as shown in the previous picture. How does a tailings pond look like? In general, it has the coarse tailing sand, which I just showed in the picture, and above which you have fine fluid tailings, which are floating in water, which eventually settle down over time to form mature fine tailings. But these mature fine tailings still contain about 30% of water, and this water has to be expressed or removed over time before before the tailings ponds can be reclaimed. Because the reclamation of tailings pond in any mining industry, we disturb the area, but the area has to be returned back to the um, public in general, because the public owns those lands. In a way, the nation owns that land, so the land has to be returned in as close as a natural form as possible. If it takes, like if there's 30% water in the mature fine tailings, it can take about 150 years to drain this water. And the problem with soft tailings, such as the fine fluid tailings and mature fine tailings, is that they are not trafficable because they don't have enough shear strength. So if they are not trafficable, then they cannot be reasonably reclaimed. This picture shows a cross section of a tailings pond that I'm talking about, wherein we saw that those are compacting this side of the dam. The dam has to be built to hold all the tailings behind it. This is the beach that I talked about, the beach that runs for many kilometers. And then you have the fine tailings suspended above the beached tailing sand, and then water on the top. And all of this is being held in several tailings ponds as the operations proceed. One of the reasons why beaching is possible in oil sands is the fines mixture, or the fines content in the mixture. It allows for the sand spaces to be filled and provides natural shear strength to it. So that basically allows you to beach the sands behind the dam structure. Next slide. Right. So then the dams are a problem, right? In the end, you cannot have dams all over the area, because if there are dams, it means that there is liquefiable material that's ready to flow behind it. And if you have liquefiable material that's ready to flow, you cannot leave it for nature to take care, and therefore dams need to be decommissioned before the land can be returned to the public. Within the oil sands, there are about 243 dams. About 30% of which have an extreme consequence classification, which is based on the amount of loss of life, or or and environmental and cultural impacts, and economic and infrastructure and property impacts if that dam was to fail. About 30% of about 25% are very high and high consequence dam, and equal number are significant consequence dam. There are regulations that have been developed in the recent times to basically guide operations of these dams and the closure of these dams, and those are both being developed by the Alberta Energy Regulator, which is the local or the provincial body that regulates the oil sands industry, and the Canadian Dam Association, which basically regulates the dams across the across Canada. This is a snapshot of one of the sites. This is about I'd say give or take 60 kilometers by 80 kilometers mine lease, wherein the various dams are shown. And as you can see, there are all these mine sites are scattered with significant high and very high risk dams, or significance dams, which need to be taken care before these mine sites can be closed. These dams are holding significant amounts of tailings behind them. As you can see, in 2014, it was holding about altogether 1,100 million meters cube of coarse, fine, and water tailings. And in 2022, that number had grown to about 1,400 million meters cubed. Coming to all of this that I've spoken about so far, which is the mine operations and the storage of the tailings as a consequence of these mine operations, result into an operating mine site, which most of the mine sites look like this at the moment today, which basically consist of tailings facilities and associated dams, the overburden dumps that I talked about, and the mine pits themselves. Here's an example of an active mine pit and the processing plant. But they also consist of small isolated watersheds that have been left behind where area has not been disturbed. And then containment of extreme events is required when a mine site is operating. There is a mandate of no release of water off site, meaning any water that falls onto the mine site naturally or is being brought into the mine site from major water bodies for processing has to be stored onto the site, and the maintenance and repair, such as the erosion of the features, have to be managed actively so that the mines can operate safely. However, these mines, as I said, have to be returned back to the public and to the nation as a natural, as natural as a possible landscape as it existed before these mines were active, and those will only be possible when these mine pits are backfilled, all the dumps are stabilized, the plants, the processing plants are dismantled and taken away, tailings and consolidated water are dewatered into solid landforms. But I said that some of the fine tailings would take about 150 years to dewater, so that's a challenging a problem. Water cap tailings are put into former mine pits. All the watersheds are interconnected using conveyance channels that have enough conveyance capacity and robustness to convey extreme floods. And these have to be self-sustaining, meaning that they do not need any active care because there is nobody to care for it. It's no more an economic resource. It's not producing anything at that stage. So it has to be a self-sustaining landscape that cares for itself. That brings me to the closure part of the oil sands mine. So far, what I was talking about is the story started in 1978 with the first production of the first barrel, and it continues till today and will likely continue until 2100. But the oil sands have to be closed in the next 100 to 1,000 years, and that's the timeline they are looking at, which might sound unreasonable to a lot of us, but that's what the guidelines are. And these oil sands mine closure are being planned and are being operated because most of the mines are at a mature stage. Most of the tailings ponds are at a mature stage, and therefore some of the mines are coming up for reclamation, and some of the mine leases are coming up for closure in the time frames that I talked about. But the challenge, the status is known, but the challenges are many because the stakeholders, which is the operators, the regulators, general public, and the government, the expectations of all of these people are very, very high. And the expectations are that, oh, sorry for that, that the hydrologic regimes in the pre-mining conditions need to be restored. The reclaimed sites need to provide sustainable aquatic and terrestrial ecosystems as they existed before mining. And then the robust, the landforms need to be robust from physical stability perspective and geochemical stability perspective, and need to be robust throughout major hazard events like earthquakes, or need to withstand those. And as I said, they should not, or they would not need active care or minimal maintenance with a design life of 1,000 years and more, which starts to sound really unreasonable, because nobody of us will be there to see how these evolve in 1,000 years from now. What are the reclamation objectives? Again, the closure landscape needs to be self-sustaining. It needs to integrate itself into the surrounding natural areas. It needs to establish the boreal forest, upland, lowland, wetland kind of ecological system. It needs to yield water at a suitable amount and suitable quality. And it needs to be planned in consultation with the stakeholders and has the capability equivalent to pre-mining. I'll briefly run through the closure conditions of these and then show you an example of mine closure that we have been working at. What does ARK, which I work for, is an engineering consultancy. They work today with the operators or the oil sands mining operators, doing all the engineering aspects, including civil engineering, hydrological engineering, process mechanical, electrical, and other disciplines. But also we are helping advance the closure of oil sands as well. In a closure landscape that will exist in future, the main components will be end-pit lakes, which are required to store the water that is drained from the landform, the drainage channels, which will convey that water to these end-pit lakes and to the environment, the reclaimed in-pit landforms, which were former mines, the reclaimed overburden dumps, which are storing all the overburden material that I talked about at the start of the talk, reclaimed tailings pond that I spent a little bit time describing, and all the associated dams. Although the sequence is not like I'm not going to speak about these components in sequence, because although I arrange them with their importance, but I'll speak about the ones that are being reclaimed first, which are the reclaimed in-pit landforms, which were former mines, and the tailings ponds and the dams. One of the problems with the tailings ponds is that they are storing a lot of water and tailings behind the dams that they are contained with. This will continue for about 15-20 years, depending on the life of the mine. And then the challenge is that if those need to be reclaimed, then within a very short amount of time, these tailings and the water needs to be managed, which actually is the biggest challenge, because this water management, there is not enough space to manage all the water that actually is contained within these sites in the current time. Then there is the problem or the challenge of the geotechnical stability. If nothing is stable geotechnically, then it doesn't matter at the end of the day. Things have to stand on their own, or they have to be structurally sound for them to be able to withstand any catastrophic events. Therefore, a lot of work is being done using CPT data, estimating the materials being deposited into these structure, and development of reasonable models over time, and also looking at settlement of the fine tailings and the consolidation rates, and also the liquefaction potential. The closure plan, one of the biggest topics that I've been delving into and spending a little bit time, is the dam delicensing aspect within the closure drainage plan assessment, which actually needs to, which actually deals with understanding how the capacity of these dams to store the water, staging of the site closure, which includes the interim conditions, therefore understanding managing of the dam delicensing and closure while the mine operations are active, and also them as a part of a key part of the landform closure design as well. The challenge, again, I've touched on this already, but the challenge is that these dams need to be physically stable and geochemically stable. But once that is achieved, then we need to or the people working in the oil sands industry need to understand how the landforms that need to be constructed behind these dams that have been closed can be constructed. The infrastructure needs to be maintained and rerouted during the construction itself. The dam safety that can be maintained during the capping stages, and after all, the economics of it, because that would also play an important part. Can we move the bar? But it's okay actually. This slide basically deals with the definition of the dam itself, and the key definition is that the Alberta Energy Regulator basically defines anything that stores 30,000 meters cube or more of liquefiable material, and that has about 2.5 meters or greater height from the base of the lowest point on the air side, or the base of the pond itself as a dam. And then it obviously needs to exist for the a purpose of storing material that can flow. But what is the dam closure criteria then? And the closure criteria will be, and briefly are being developed as time goes, are that ponded water is not available and cannot accumulate behind these structures. The contents cannot flow, obviously, which is any liquefiable tailings cannot flow through a piping mechanism, and conditions will not develop in the future that could violate all the previous three criteria, meaning it's for the current, but also for the future. And then once this is all taken care, then the long-term care needs to be initiated, wherein these structures need to be robust enough so that they can withstand flood, earthquake, multiple consecutive wet and dry climate cycle, surface settlements, erosion, any anthropogenic activities, because we cannot control all of that, and natural animal activities like burrowing, which can cause piping failures. That brings me to the reclamation of the drainage channels and overall landscape as a part of the closure landscape, and the overburden dumps. One of the most important things with the reclamation of the overall landscape is that oil sand industry is, like in Canada, is a part of the boreal forest, which is a water deficit area, meaning the potential evapotranspiration in the area is greater than the precipitation itself. It has large groundwater recharge. It has extensive wetland network, which is inefficient in draining the landscape. It has small and variable surface runoff, and it has a tightly coupled surface water groundwater system. The drainage channels, therefore, that will drain these reclaimed landscapes or closure landscapes need to have enough capacity to convey extreme floods, limit rates of natural erosion, limit risk of rerouting during extreme floods that can happen, which is channel avulsion, of course. They need to control the phreatic surface so that it doesn't lead to liquefaction type, dams type failure, and account for natural morphological changes like widening of channels and meandering of channels. Of course, when all of this is considered, then you need to think of the ecological design, meaning use of the natural species, and also understand how the species are going to change over the time, especially in the times of climate change. That also includes the importance of the ecological setup for the native people who basically have lived in these lands for thousands of years. As I talk about the ecological species or the ecological design, as we can see, like in the boreal area, there are tons of species that are available, and the tons of species come from the fact that it's a lightly sloping, gently sloping landscape that has upland vegetation, intermediate vegetation, and wetland vegetation. There's tons of research. There's a serious amount of work being done in cataloging all the species that can therefore be used in the post closure landscape. And finally, the wildlife needs to be restored, which also means that understanding the habitat requirements for the native wildlife, the habitat connectivity itself, so that they can move freely through the reclaimed landscape, and the most important animal, which is the beaver, in these landscape, they basically like creating dams for themselves and living in water. Those considerations are also very, very important, because they can basically form dams without any real intent on part of the reclaimers to have dams in the landscape. And then I'll talk about the last but not the least, the most important, I would say, feature as well, which are the end-pit lakes, which store the water and are and mimic natural lakes that existed before the mining started. The problem with end-pit lakes, end-pit lakes sustainability is that, again, this is a water deficit area. So the recharge needs to reach all the lakes in a reasonable fashion for the water budget to be right. As you can see, naturally, many natural lakes actually have declining profiles during droughts. 1990 to about now was a drought period in Alberta. So natural lakes can decline and recover, and that is also applicable to the end-pit lakes. But in general, if the precipitation was to be on a deficit side due to the increasing temperatures in like under climate change conditions, then you would basically have an end-pit lakes that will not be sustainable from both water budget consideration, but also won't be geochemically sustainable, because there's not enough water to dilute the chemical constituents. Having put forward a lot of material so far, the most practical way of reclaiming and closing these mine sites actually is to plan for mine closure, which actually it includes determining the objectives, designing, and then developing management strategies, implementing that, evaluating and adjusting as we learn, and learning and redoing the same adaptive management process over time with other mine sites. That brings me to an example of one of the mine sites we have helped, or this is not the one that we have helped reclaim, but it is a similar mine site that is, like in this case, is a tailings pond that has, where you can see the sand beach and soft tailings deposited at the end of mining. This is when the mine was being infilled, and that was around the year 2000, so that it can have a base of material over which the reclamation surface can be developed. This basically shows the development of the uplands and the lowlands and the transitional hydrological features within that mine pit, which was being reclaimed. And then this basically shows the current day status, where you see that the site is fully reclaimed with vegetation, albeit it's still not certified as reclaimed, but it does show a lot of progress and a lot of success of implementing all the learnings that we used to basically reclaim the mine site. And basically today it's in the stage of establishing wildlife habitat and connectivity. And the hope is that within next 10 to 25 years, it will be fully reclaimed and certified. Some closing thoughts. Oil sands mines are large operations that contain major economic opportunities, but also major geoscience and hydrological problems, which are being dealt or are being dealt with closure plans that are being developed with with a combination of geomorphic approach and traditional armoring for the dam aspects. And current performance of large-scale reconstructed channels is unknown, because those haven't been constructed, because those will only be constructed when the entire mine leases are reclaimed. But there needs to be a recognition that, given the complexities and challenges of closure, these will be eventually developed with the knowledge that's being gathered. And if eventually, hopefully, these mine sites will be returned back to their pre-development capabilities. Thank you very much.
Thank you, Mr. Nagare, for a wonderful presentation, and especially the amount of work that you have done for the protection of the environment. That's really very interesting and very, it shows the importance that is laid to the care of the environment. Now, I'll start with the questions which we have received online. Are there any potential areas or availability of oil sands areas in Indian territory? From Dr. Sudesh Wadhavan. Are there
I was talking to one of the audience members, and I was told that there are certain amount of areas in the state of Rajasthan where check. No. That in the state of Rajasthan, there are I'm not sure how much or how extensive, but I've been told that there are certain amounts of deposits.
Okay, thank you. The next, please go back to the questions. What is the age of oil, sand, and deposition of bitumen?
I mean, the deposits themselves are Cretaceous period. But there is an unconformity in the between. So there is a bit, I'm pretty sure that there is not a full certainty about it, but these are the Cretaceous period depositions.
Okay, here, in fact, I also was very curious about this because the literature which I have come across, it says about the subcretaceous unconformity is the base of the formation. And this lower McMurray and upper McMurray, these are the two formations, and that Wabisca. So these two, do you mean to say that these are confined to Paleogene?
I would say so, yeah.
Because I don't think it goes into Neogene. Thank you. Similar mining in other parts of the world.
I believe there is some in Russia, in Kazakhstan, and in Venezuela, but not at this scale, actually.
Okay.
This is unprecedented. Actually.
USA, you have Utah.
Some, but you know, the problem again came back to the tailings management that I talked about extensively. Due to the tailings management problems, a lot of operations in the US were actually scaled back. So there are some, but the idea is to develop dry tailings as much as possible. But that's also a challenge. And the water and the soft tailings limit the amount of operations in the states, actually.
And I think the advantage of Athabasca bitumen deposit is the presence of water, which makes this separation of sand from bitumen.
True, it does. But then that's the advantage in terms of the resource exploration and the resource development. But the problem again comes back to the future of it, which is the tailings management, which also that ends up developing a lot of soft tailings as well, which need to be reclaimed in the future. So it's a question of the economic advantage today,
yes,
versus the challenges of
tomorrow.
Tomorrow.
But in a case, like in Venezuela and all that, where it is not water wet, so I think the cost of mining is a little more.
Absolutely. So some of the deposits are, then they basically don't, whatever deposits don't have the water attached to it, they need to be then processed using other
technology.
Technology
For separation. Thank you. How about contamination of groundwater in the mine tailing areas? How is this taken care of? What are the remedial measures? Again, Dr. Vadhavan.
So I basically do a lot of that work. There is definite, so wherever we have industrial activity, there are going to be some environmental impacts, but these are actively being managed. The active management includes monitoring of the groundwater around the mine sites, as well as tailings ponds. And then there are either slurry walls, which are cut-off walls, or active extraction of groundwater, and which is pumped back to the tailings ponds in an attempt to not let the contamination go migrate off-site. But if it migrates off-sites, then there are regulations that basically mandate the operators to basically go into these areas. There's of course a regulatory process behind that, but go into these areas and remediate it. The most common form of remediation is basically pumping it back to the tailings ponds and containing it. And the reason for that is because most common contamination, if any, is brine or salt, and it is extremely difficult to treat salt and brine in situ, right? Everything else you can actually treat either using mechanical methods or bioremediation. For an example, if you had a contamination from the oil itself, you can basically use oil. You can use thermal methods or bioremediation to basically treat that contamination. But when water is contaminated by salt, then basically the only way you can do it is basically pump that out, bring it back to the site, while allow the nature to take its own course to basically restore the area that was contaminated through natural healing, if I can call so.
The literature I have come across, if I'm right, there are heavy metals like nickel and vanadium found in the sediments.
But these migrate so slow. So you're right. So that's a question of that comes back to the mine reclamation and closure part actually. So there is heavy metal contamination in the water that is being contained in these areas, and that needs to be taken care of. So one of the ways it is being done is one of the byproducts of oil sands processing is what we call petroleum coke. So petroleum coke is being used as filter to filter out the heavy metals, some of which are obviously toxic, but they migrate. Very little has been observed offsite that has migrated, or there are not many examples of offsite migration. And even if that is the case, I would say the way it is being handled is again by pumping and treating on the surface, and then either releasing that treated water to the environment or storing it back if it is not treatable. I'd like to mention one of the most important things. If you look at global mining operations, right, and the standard that oil sands, like the province of Alberta holds oil sands operators to the environmental standards, there is a huge gap actually. Oil sands does tremendous amount of work, or the oil sands industry does tremendous amount of work to ensure that there are environmental impacts of all sorts. Like we cannot discount environmental impacts from economic activities. Wherever we have economic activities, we have environmental impact. But oil sands in industry does tremendous amount of work to mitigate as much as possible and continue to make advances in water treatment area, especially for the specific problem that you talked about, in order to keep up with those regulations and the high standards they are held to.
Thank you.
I hope I answered your question.
Yes, thank you. This is since Mr. A.B. Panigrai's question, since the bitumen is at 7% cutoff, how much percentage of original area is restored? How many years it takes to rehabilitate an area?
So the question is interesting, right? Like, I mean, it's a debatable question in a way for the oil sand industry themselves. Most of the mines are still active. Most of the tailings ponds are still active. Some of them are reaching their end of life where they will be reclaimed. There are only two examples right now, which will be one. We said that there is about 1,000 kilometers squared of area which is disturbed. There are only two mine sites that have been constructed so that they can be reclaimed in the near future. And I'll talk about the timelines. But in general, it will take hundreds of years, if not thousands, to achieve full closure. But there is a caveat in that. And the caveat is this, that the biggest problem with the mine restoration is that, or restoring back it back to nature, is that it's the water chemistry problem. So if the oil sands industry, like right now, it seems like it will take a long time. But let's say, for an example, the regulations become strong enough in the future, wherein they are mandated to treat their water, all of the water that's on the site, then it's highly likely that those timelines will be shortened, because now there is active treatment that will be involved. Now, is that practical or not and economically viable or not? We don't know at this point,
At this,
right?
yeah.
Because it's highly possible that we will make an energy breakthrough, because these are all energy intensive
Right.
processes, and
Yeah.
that's why they're very expensive. But it's highly likely that we will make an energy breakthrough in the next 50 years, which will solve this problem and the contamination problem globally, actually, because there is a problem, the industry-wise problem, or the industry sector-specific problem here that we're talking about. But the water contamination problem in all sorts exists globally, which is not being dealt at the moment in a reasonable way because of the energy costs.
Right, right.
I hope, like I
Yeah.
basically answered it in a philosophical way, because there is no straight answer to that.
I get it.
Yeah.
Yeah, I get your point. Yeah, thank you, Mr. What is the impact on people working in such processes in terms of health hazards, if any?
I would say, I mean, again, as I said, we are like the oil sands industry is held to very high standards. The safety standards are very, very high as well. Accidents are taken. Oh, I'm sorry for that. I was basically just interacting with Dr. Farooq, but I need to interact with the audience as well. So, can you repeat the question again? Sorry. For the human impact. See, the oil sands industry, again, like this is again the same way. I mean, the impacts I would say are minimal unless you are in contact with the oil products themselves. There are, I'm not aware of the quantification on honestly of the health hazards themselves.
Mhm.
But what I'll say in summary is that the industry is held to very high standards, and it basically comes true to its commitments most of the times. Now, there are definitely different types of hazards, which again, the quantification of that I'm not completely aware of to answer that question fully.
Yeah. Have you analyzed uranium content in these rocks, Mr. R. Mahanti?
I myself have not analyzed that for sure, but I know for sure that the equivalent of the Geological Survey of Alberta had done the study. They had found some content in it. So there is some radioactive content in it. But to be very honest, again, that's one more area I cannot.
I've just, yeah, please. Please. Yeah. You can come here. Come here.
I have a question on this mine closure plan. Mine closure plans are mandatory in India. While opening a mine, we prepare the mine closure plan. Simultaneously, we apply to Director General Mine Safety, Dhanbad, who controls 600 coal mines and about 1,000 metal ferrous mines and all those things. And in mine closure plan, a lot of money, because mine has to be brought to the original shape, including the vegetation and all these things. So therefore, the mine closure plan shows, I'm just telling Indian concept how much and what is Canadian concept.
Absolutely.
So how much of total mineral is extracted, how much of overburden is extracted, and suppose say, let us say aluminum or let us say iron ore, etc., wet process. So by which the metal content is upgraded and the gangue, that is silica and alumina, are removed and deposited in the tailings dam. So the total budget is prepared. We have an annual plan and we have a cumulative plan. Annual plan means something like 10 crores or 15 crore, where a separate bank account is opened and it is deposited, because the private mine owners may run away after the mineral is exhausted. So like that, the total money is deposited, then it takes 3 to 4 years to backfill the area and bring it to the original shape and vegetation. Because these are just compulsory, and otherwise no mine operation will be allowed. And are the operations in Alberta similar to this?
Absolutely. So mine closure
Yes, mine closure.
is mandatory,
Yes.
right? But it's being done. So what's being done is being done by the private operators because they are mandated to close the mines and bring the land to its
To the original shape.
Yeah, to the original shape as discussed. Is there a separate fund that's being created? Actually, there is, but I don't think that those funds are enough to uh, cover the costs of mine reclamation and closure. What I mean by that is these need to be done when by the private operators because they're mandated to do so because they are also earning money from it. So the concept is that as a part of the operation, you have to do the mine closure and mine reclamation. There are thousands of examples in the US, for an example, like what you said, which is really true, that the private mine operators finished the mine operation and then they ran away.
Just in
or they declared bankruptcy, right? That happens all the time. But I would say that the progress that we have seen in Alberta, the mine operators have taken mine reclamation and closure very seriously, and it's being done actively. Now, it's very difficult to project into the future what might happen, right? But oil is such a resource. I think one of the advantages here is that oil is such a resource that in good times it provides a lot of surplus. So these companies then transfer reasonable amount of money towards mine reclamation and closure, and it's being done in parallel. So I believe as long as the watchdog or the regulator basically keeps the pressure on, like to say it in very simple terms, the reclamation will continue. But as you said, sir, who knows about the future? What might happen?
Yes.
And there are very few, because mining is a very old activity, a very old human economic activity, and there are very few examples of reclamation and closure. Most of the examples, even in the States, even in US, where you expect, given the science that Environmental Protection Agency or the EPA that we know by, right, has developed, even there, the companies have ran away, and there are thousands of mines, and they have left the mines to be reclaimed using public money.
I'll just, in Indian condition, it will just not be allowed to operate because whatever is the mine closure that is added up to the operation, then per ton cost is worked out. That is done in cumulative basis.
That's
so
exactly the case.
Because our statutory regulations are quite tough, otherwise mine accidents are rampant.
That's exactly the case in Alberta as well. But the problem is that the operations will continue for another 100 years.
Okay, this problem. I had another problem with regard to the telling, with regard to stock of tellings. Suppose you prepare a telling pond and you make a dam. And telling pond, stores what? It's the processing waste, etc. So once that is full, so you have either to increase the height of the dam, say another 4 or 5 years, and once that is full, you go for another dam, and you have to get statutory clearance and all these things. Is it done in a similar way there?
Absolutely.
Achha. Okay. My question is over. Thank you. Please.
Thank you, Doctor. It's a real knowledge to us in India because that size and type of mine we are not aware. And I am Dr. Upadhyay. I have worked in Ministry of Environment and Forest, Government of India. I am a retired person. And I have been involved in the oil extraction, exploration, and the CBM, coal-bed methane.
Yeah.
Those are there in India. So
yeah.
looking at this size of this mining, it is, if you apply the Indian regulation, it is just not possible economically it can be made viable. Smaller mines in India, there is now condition that whole pit, whether it is OB or the trailings or the water body, it should be totally impervious pit has to be created, HDPE line. Such a big mine, 100 square kilometer, I think.
1,000 square.
1,000 square kilometer. It will not be economically viable. But I know the Canada has a different geography. Population is not there in those areas. And even groundwater which goes, there will not be people for drinking also. So that is the safest.
But there is no. You're right. Actually, this is an interesting. Like this is again comes down to a philosophical thought, but also what nature provides actually.
Yeah, that's right.
This
My only, I wanted some clarification. Is there any analysis of heavy metals of different layers, which is being dumped as overburden of different layers? And what happens when there is a little melting, when the temperature goes 25, 26 degree, sometimes it is -8, -9. When the C1, C2 gases, they come out, is there any safety precaution or any risk was involved? Some accident has happened and these contamination of heavy metals, whether it has gone into the tailing ponds and birds and other things, because Canada is known for very, very good birds and zoofauna and fauna. Is there any study on those tailing ponds? What has happened to them? Because treatment, I have not seen any treatment. It is being contained. You also said it is
Absolutely.
just contained.
Absolutely.
I think there must be some progress in doing these type of studies. What is happening to the fauna and flora in the tailing dams, and how seepage is there of the heavy metals, and what is happening to methane and the benzene gases, which they get emitted when the matter is exposed, and the bitumen gets melted. Is there any incidents like this?
So
Thank you.
I will answer the insignificant ones first, right? And then we'll move to the significant one, because I need to answer this question carefully because I've got a regulator asking me that question. So I know. A formal regulator, right? So yes, there are methane seeps, either natural or during operations, or from the storage, as you talked about. These methane seeps are being constantly studied and are being quantified, but they cannot be. I mean, they are mitigated by either covering the areas with low permeability materials where available and as possible. But in many cases, and as you would know, that if you go to the Texas area, for an example, methane seeps are uncontrolled in most of the operations. So some of the uncontrolled methane seeps happen in the oil sands as well. And I would say that it would be really naive or would not be true to say that there are no methane seeps that happen. So there are certain things that happen, but they are being monitored and they are being mitigated where possible. About the heavy metals, Dr. Farooq asked me the question, or one of our audience member asked the same question. I'm pretty sure that there are no examples of off-site migration of heavy metals, or if there have been any, they are being dealt with, because the regulator is as stringent in Alberta as you stated for the Indian operators. The stringent, because the laws are so stringent, because the regulations are strong and they're being implemented in a fashion that they need to be implemented, that all these sorts of accidents, if you can call them, because accidents do happen. Like it's not that, like when we are doing an economic activity, accidents are bound to happen. So nobody wants to contaminate the environment beyond the economic activity boundaries that we work within. But when these accidents happen, the operator is mandated or is responsible for the entire cleanup. I'll tell you that recently there was a seep from a tailings pond into nature. I cannot disclose the information, but just to answer your question, just as as far back as six months ago, there was a major leak which was detected. The boundary was extended. They were mandated to take care of it and account for it. And they've spent in the past 6 months, I would say, hundreds of millions of dollars at addressing that problem. And I'm pretty sure that when you were a regulator, same sorts of cases would have happened in India as well, where accidents do happen, but then the regulator mandates the operators to fix the problem in the simplest words it can state so. Yeah.
Thank you.
I would like Dr. Nagare's email to be given to me. With his permission, I would like to have some discussion with
Absolutely.
Okay.
you. Are expert, so some knowledge gaining.
Absolutely. And vice versa.
Thank you. Thank you, Mr. Nagare. And now I have to do the unpleasant task of telling you that question.
I have just one question.
Yeah.
Are you not?
I'm sorry. Just one question. Okay, please. Please.
Shall I?
Yeah, one question.
Are you not doing this reclamation concurrently?
No, absolutely. So as I said, there are two examples of so the simpler ones, which are the overburdened dumps. There are more examples of it, which have already been done and certified. Certification means when the land is being returned to its natural state, that's when the regulator comes and says it's certified reclaimed. So there are certain examples of that, of the simpler landforms. The more complex landforms, which are the mine pits themselves and the tailings ponds, there are two examples, and that's because they are the only ponds that have finished their life of mining and have been infilled and now have been constructed. And if Rob Woods is on the call here, Rob and I basically have worked on these the construction designs of these. They have been constructed and vegetated, but have they been certified reclaimed? Not yet. But to answer your question, is there concurrent reclamation activity? Absolutely.
My second question is, what do you use as agent for carrier in the froth flotation?
Can you say
In
that again?
froth flotation, you are extracting oil. Froth flotation. So what is the agent you are using as carrier? Froth flotation.
Caustic soda.
Oh,
right.
Well, thank you, Dr. Nagare. Now, okay, one brief question, and we are going to close after this, please.
Yeah. Just only for my clarification. I just yeah. As I understand, this is a mixture of oil sand is a mixture of bitumen, sand, clay, and water. We are extracting bitumen out of it, and we are recycling the water. The only thing, the sand and clay are going to outside pond. The tailings.
No, but also water as well.
Water also, we're also recycling the water.
Yeah,
Now,
but if you are
my question,
recycling the water.
My question is, in the process, we are generating huge amount of sands.
Correct.
Whether, just for my clarification, whether this sand is being utilized by the construction industry in Canada?
No, the sand is being, because this, where did the sand come from? It came from the digging of the mine pits, right? Now you have to reconstruct the landform again. So you need material. So why would they give it to anybody else? They basically store it in the tailings ponds or mine pits until, and they again use it to build back. Because if they have to build using new material, then it's economically impossible. So they basically store all this material in different areas within the mine site. That sand comes back, and that's used to reconstruct the landscape.
I'm sorry, but the time we have borrowed from Dr. Nagare for this evening, we are running out. We have run out of the time. 6:30 to 7:45. We have crossed 7:45. I know the curiosity of our delegates here cannot be uncontrollable, but then we have to call it a day. So we conclude. I request Mr. Jain Das to conduct the vote of thanks.
Thank you very much.
Thank you, Dr. Farooq. And I must thank our speaker, Dr. Ranjeet Nagare, for his excellent talk, and also the very good deliberation and interaction online as well as offline. I think we had indeed an excellent session. And to make it more sweeter, I now request our president to come to the dais and offer a small memento to our speaker, Dr. Ranjeet Nagare. It's just an appreciation and a token of love. Let's give a big clap. We are also presenting a book on geology of Odisha and mineral resource of Odisha, and along with our latest bulletin. And we request him that if he finds time, we publish our bulletin every year twice. So we would request you a kind of an overview of your activity so that we can publish in our bulletin. That would be interesting. Oh, sure. Thank you very much. Now, so thank you. The last part of the program, I would request our Secretary General, Sri Trilochan Mansa, to offer a vote of thanks. Please.
Thank you, Mr. Das. First of all, I would like to thank Dr. Nagare for giving a very vivid presentation of the occurrence of the deposits, how they are mined, how they are processed, how the reclamations are being made. And not only that, he also very patiently answered all the questions from outside as well as those questions were raised from the hall. Actually, he had after we came to know about him, I had just given him a mail of how many days he will be staying here in Odisha and all that. So as soon as he arrived in India, he made a call to me, and thereafter it was taken over by our Vice President Sujit Mohanty, and he was in constant touch with him. And Dr. Nagare made it a point to be here in time. So I thank you very much, Dr. Nagare. And I would also like to thank all the distinguished participants of this lecture today. They are from different disciplines. Apart from the members of SGAT, actually without whom this lecture wouldn't have been a success. And I will like to thank our president and both the vice presidents. Of course, one vice president could not make it to the venue because he had other engagements in a parallel way. But when I got the information about Dr. Nagare that he will be coming to India and also to Odisha, I immediately informed my president and vice president, and all of them were very keen, and they readily asked me to arrange the talk in a possible way, how it will be. So their interest in this talk was much more, than I thought of. So my thanks to our President G.S. Kuntia, Mr. Sujit Mohanty. He was in constant touch with Dr. Nagare and our other Vice President, Mr. A.B. Paningrahi, and Mr. Jayan Das, our Joint Secretary. He made it a point to see that this meeting is very success, and for arranging this Zoom link, YouTube link, and all those things, and arranging personnel for that, all these things, and also moderating this meeting. He has done a lot of things. My special thanks to Mr. Jain Das and Dr. B.M. Farooq. He took up the moderating of the question hour. My special thanks to Dr. Farooq. And our constant companion in all these programs is our Mr. Tapos Raut, who does everything for SGAT, right from collecting memento to arranging these high tea, everything he does. And we are also supported by the personnel of the Geo Image System Private Limited, particularly those boys, Ashok and Prabhakar. My special thanks to them. And in fact, my special thanks goes to Dr. Lalu Mansingh, who is very much here. And he is the person who first informed me that Dr. Nagare will be in India, and for a few days he will be in Odisha. And that is how we came to know about Dr. Nagare, and we contacted him. So it is him actually, Professor Lalu Mansingh, who has introduced Dr. Nagare to us, and we could go through this evening. It is only due to him. And also I have observed in previous DLS that we have conducted, he makes it a point from join to those DLS from Canada also. So my special thanks to you, sir. Yes, sir. Yes, sir. Yeah. And along with Dr. Nagare, I would also like to thank the parents of Dr. Nagare, his mother-in-law, his wife. And I know that when they have come to Odisha, they definitely have the program of visiting Lord Jagannath, visiting our Black Pagoda, Konark. In the midst of that, they also made it a point to be with him in this hall during his talk. So my special thanks to you all. So thank you all.